Today we're going to talk about SystemVerilog. I kind of have renamed this a little bit, just saying SystemVerilog implementation made easy, and that maybe should be easier. So with that, so this is a slide that I talk about. You know, back in the late 90s, what I was a consultant for Mentor Consulting, and the big thing we talked about was IP reuse. And the concern at that time was that manufacturers keep doubling the size of the silicon every 18 months. So whether it's an ASIC or FPGA, you can put twice as much logic on every 18 months. And the concern was, at that time, we thought, hey, we're not going to be able to design enough logic to fill up these ASICs. Well, it turns out that engineers are pretty clever, and we just figured we can put, you know, 2 FPGAs on one, or we can reuse a lot of components. So that part was useful. But what we didn't really anticipate yet was that the problem was going to be verifying all that logic. And you can kind of see that in this graph right here, that if you look at ASIC projects, in 2007, there was probably twice as many designers as there were verification engineers. By 2012, it was approximately equal. And if we looked at 2019, I would say there's probably more verification engineers working on any project than there is actual designers. So it's that verification productivity was the thing that it turned out to be really hard. In the FPGA world, you know, the silicon vendors have their SoC builder, and you know, they're just pulling on more and more logic. You know, from Mentor, we have high-level synthesis tools. The question is, you know, how do we close that verification gap? That gap between, you know, we can put all this stuff on there, but can we make sure the device works? And, you know, how do we do that? So, you know, one of the things we see is that people say, well, with FPGAs, you can just get them in the lab really quick because they run really fast in the lab, and we can do a bunch of debug there. But there's a couple of inherent problems with that. First of all, yes, you can run it really quick, but it takes a whole lot of time to synthesize and place and route and do a bunch of other things. And also, the debug in the lab is really difficult. You have very limited number of internal signals you can look at, and it can be really hard to figure out what's happening when you do see things that don't match up. So the debug is really unpredictable. And then, you know, most of all, it comes down to this idea of, you know, you don't necessarily want to find bugs later in the design cycle, because every phase that you go down in the design cycle, it's an order of magnitude more expensive to fix that device. So it really comes down to, how do we close that verification gap, and what is the technology? So a lot of designers say, hey, if you could just make your simulator run faster, you know, that would help us. And that kind of brings me to this quote from Henry Ford is, you know, sometimes if you ask the people what they want, maybe they're not going to tell you the best solution. So is there something that we can do to close that verification gap that is not just a faster simulation, that's going to solve the problems in a more elegant, more efficient fashion? And so if you look back at the ASIC world in the late 1990s to you know, early 2000s, they came up with a number of different methodologies to try to address that. So the traditional methodology was, you designed your chip in, say, Verilog or VHDL, You probably did your test bench in the same method. Your test bench was based on a verification plan, either a formal plan or loosely based on the functional specification. And you said, I have this feature. Let's say I'm transmitting packets of data across a noisy channel, so I put a CRC on the end. My test bench was, I'm going to send good data through, calculate the CRC, send it, and the correct response is that the chip receives it and says it's good. So that's the easy thing, is to send good packets. Then you want to start testing failure cases. So you send a bad packet, you corrupt a bit of data, and then the correct response from your device is that the CRC doesn't match up with what was transmitted. You got to resend that packet. So that's fairly easy. But now you come to all the weird boundary conditions. Does my device continue to work if I get 2 bad packets in a row? What about 3 bad packets in a row? What about good, bad, good, bad, good, bad? You know, all these weird conditions that you have to think up because you're creating basically directed tests that test it. And for the most part, if you're doing a self-checking test bench, you are basically stimulating all the inputs and you're observing the outputs to say whether or not the test passed. So the first method that they came up with is something called assertion-based verification. And what assertion-based verification is that I bind assertions to different points within my design. So now I'm doing white box testing versus black box testing. I can observe any internal signal I want to with those assertions. Those assertions are also, they're temporal in the sense that they say, when I see this internal condition, then I want to wait 5 cycles and I want to check for this. And then I want to wait 3 to 7 cycles and I want to check for this. And then I want to wait and check for this. So they're good at doing temporal sequential protocol checking in a way that VHDL and Verilog are not. And that's because VHDL, VISIC, hardware description language, Verilog is a hardware description language. That's what these languages were designed to do, to describe hardware, to design hardware, not to test it. The other benefit of these things is that because you put them around here, and let's say, you know, I'll put an assertion that's checking the handshake between these 2 blocks, and it says, you know, if I put out the request and I don't get to acknowledge, this assertion right here will raise its hand and say, hey, there seems to be some problem right here. So they get you to the source of the error much more quickly than if you have to debug all the way from the outside of the chip and debug backwards through the data path, backwards in time to try to figure out that the reason the data coming out was wrong was that these blocks didn't handshake correctly. And the last benefit with assertions is that you bind them to different modules. And the reason that becomes powerful is in the next generation, I'm going to pick this block up, I'm going to reuse it, but I'm going to have 3 of them. I'm going to throw away this parallel interface and I'm going to make that a serial interface. Maybe I'm going to mux those together. So my traditional test bench is pretty much thrown away. Whereas these assertions that are bound to this block, they can just move in and they don't care that they're 3 levels deep in the hierarchy, that there's 3 of these blocks instead of 1 of them. They're just going to do what they were designed to do those checks and let you know if there's any problem. So they start the process of test bench reuse. So the next thing is to say, well, when am I done? How do I know when I'm finished with my design? And that is in the traditional testing mode, you kind of said, well, I have all these features and now I've written a test for each one of those and that's when I'm done. But what we can do here now is we can say, for every one of these features or for every one of my test ban objects, I can say, hey, I have these 4 assertions and other coverage type objects that if those things are activated, they never fail, then this requirement is covered. The next requirement is maybe these 3 test coverage objects. And if those are tested, then that is finished. And so it becomes a measurable thing where I can say, I've got enough coverage, I'm done. So that was functional coverage. The last thing was the idea of a constrained random test bench. And so now instead of a directed test where I've got to go through every feature and I've got to say, you know, I'm going to generate this data and I expect to see this result. The constrained random test bench says, you know, I'm sending these packets of data with a CRC, but my real specification at the system level is those packets need to be reliably received in a environment with a 10 to the minus 5th bit error corruption. So what I can do is design my test bench to say, I'm going to generate packets of data, I'm going to randomize whether or not I corrupt the data, and I can change that data corruption rate, and I can keep cranking it up till I stop receiving packets correctly, and then I can say, well, what error rate was I at when that happened? So that is this idea of sending randomized data. But we can't just totally randomize because it'll take forever to get my functional coverage up to 100% to say I'm done. So that's where I have constraints on my randomization. So I can say, you know, my packets, you know, have a variable length, and maybe that is, you know, 10% of them should be short, you know, 0 to 64 payload, and then medium maybe 40%, and large 60% something. So you put these constraints on there. And so all of this kind of developed in the ASIC world with a bunch of proprietary tools. So there was Sugar from IBM. There was Synopsys Vera eventually. There was E-Code for Vericity Specman. So all of these things were really good methodologies, but they had problems. The problems were, one, you know, it was these proprietary languages, which meant you were tied into a single vendor, single tool. It was hard to find engineers who you know, could use that methodology. You were tied to that company. If they went out of business, you were, you know, kind of screwed. If they doubled their price, you had nothing, you know, no choice but to, you know, continue to use them. And then the other issue was all of these engines that did these different pieces, the assertion engine, the constraint solver, the functional coverage gatherer, they lived outside the tool in another thing that talked to your simulator through the PLI, and that ground simulation speed down to, you know, being really slow. So in the mid 2000s, that's where SystemVerilog really became the tool of choice. And it was basically, they took this Verilog base, they added some language enhancements for synthesizability, like enumerated types and, you know, a few other things, interfaces, other things. But then they also added the SystemVerilog assertions to do the assertion-based verification, object-oriented coding. So that was kind of the C++-like object-oriented coding and the constrained randomization. And it really allowed us to move the verification world into a more structured verification process like software verification. And it did it with a standard language that, you know, we're not tied to these proprietary tools with proprietary languages. So let's go in and just look real quick at some SystemVerilog code. So this is kind of giving you a little insight into how SystemVerilog works. So the base object in SystemVerilog is called a class. And a class, if you're not familiar, is like a record type in VHDL, in that it is an object which contains data elements, but the difference between a record and a class is that not only does it have these data members, but it also has the functions that I might be interested in, operating on the data in this class with. So in this case, I've declared a class called rectangle. It has a length and a width. You'll see there's this thing called the new function, and that's what's called the constructor. These are dynamic objects in the sense that you declare a handle, and then you need to call that new function to create an actual object of that type. And then right here, I have a function called area, which when I call the area function, it will just give me length times width. So down here, you'll see I've got a class called rectangle. I've declared a handle to a rectangle type. And then right here, I'm calling the new function on that rectangle, and I'm saying it's going to have a length of 50 and a width of 20. And then I can say display, and I can say rectangle.area. So that will call this area function, calculate 50 times 20, which will be 1,000. So if I look here and get a little more, let's see, what am I doing here? Okay, so here what I've done is I have this rectangle function that I just showed you in the last one, and this is where this idea of class extension and class inheritance comes in. And this is kind of the root of object-oriented coding. So what I've done here is I've declared a new class called square, or a new class type called square, and I say that extends the rectangle type. So that means a square is everything that a rectangle is, but instead of using the new function from rectangle, I'm only having one argument called side, and the constructor for that is saying, let's call the new function super.new, which means let's call my parent's constructor and pass the side and side as the two arguments into there. So now I come down to here, and I'm declaring a rectangle, I'm declaring a square. I declared a rectangle of 50 by 20, I do that display. Now I say I'm going to call a square, I say the side is 50, but you'll see up here, that means 50 and 50 are passed into here. So, that creates that rectangle there. And then last, you'll see I say, let's show the area of a square, and it says, okay, let's call the area function of square. So I go look in square, and there is no area function. But because this thing is everything that a rectangle is, that means that I have access to the parent's area function. So it's just going to be length times width, which in this case is side by side. So you'll see if I run that code that this would come out and say area is 1,000, this would come out and say area is 250. And then you see class inheritance, it says that I've declared this thing called a rectangle, and then I've declared a square, which is a child of the rectangle class. Where this starts to get more interesting is we can start to put randomization into our objects. So when I declare a class, I can use this keyword rand when I declare those class members. And so you'll see I've declared address, data, and operation, memop, as randomizable objects. And then right here, my new function basically assigns address, data, and memory operation to those variables. It has some default values, but then you'll see right here when I declare that op, I declared a new one, and then now I'm going to run this loop, and I'm going to say assert op randomize. And the reason I put this op randomize in an assert is if this randomization fails, it would give a message saying that, as opposed to just, you know, dumping somewhere. And how does randomization fail? Well, once I start to put constraints on these randomizable things, I could potentially put constraints that contradict each other. So maybe, you know, as I'm creating things, I don't realize that I said address must be greater than 1,000, and someplace else I said address must be less than 900. And so then if I did that randomization, it would say there's no way to create an address that meets those constraints. So for now, you'll see I'm just randomizing this 5 times, and you'll see I'll get random address, random data, and I don't know why those all came out to be read. I don't think I have a constraint here. Maybe that was just, you know, my potential things are read and write, and I just got, you know, I randomly got 5 reads in a row. But now, with class extension, what I'm going to do, I think maybe I just copy pasted it from the wrong slide. With class extension, you'll see what I can do is I can say, you know, I'm going to declare a class called readOp, and it's going to be exactly the same as a memory op, but I'm going to constrain so that memop is always a read. And then you'll see you did this, and now I got all reads for sure. I need to put some writes on that last slide. Anyway, so that is kind of SystemVerilog object-oriented coding at its base. And then what Mentor did was they took that SystemVerilog language, they took the model sim kernel, and they pulled all those engines that did all those other things into that, and that is what we came out with in the mid-2000s, and we called it Questa. Rather than calling it, you know, Model Sim SV, they just decided to call it Questa. So I guess you're questing for bugs. Anyway, so SystemVerilog is the language that we're going to use. There is also what's called a methodology, and you might have heard of some of these different methodologies. So for now, ERM, that was kind of the first methodology. That was the e-reuse manual that Vericity created for their e-code specmen tool. That was the first one. Synopsys came along with this tool called Vera, and they created the Vera methodology manual. And so that manual was called VMM. That was the methodology. So that became kind of the gorilla. Everybody in the ASIC world was creating test benches using the VMM. So once SystemVerilog came along, Mentor created something called the AVM, which took that SystemVerilog language. They created a bunch of base classes for doing all the pieces of your test bench. So, you know, if you want to drive data, there was an AVM driver. If you want to receive data, there was an AVM monitor. There was an AVM sequencer to create sequences. There was a AVM coverage collector. There was an AVM, you know, just all the different pieces you would create your test bench out of. Cadence basically had acquired Vericity by that time, and they basically, for SystemVerilog, they more or less updated the ERM and called it the URM, the Universal Reuse Manual, or I don't know exactly what URM meant. So these were both methodologies that were completely based on SystemVerilog, but we were competing with Synopsys, who kind of owned the market. And so what happened was we decided we should team up with Cadence, and kind of Mentor and Cadence got together. We took most of the classes from our AVM. We took some of the coverage stuff from the URM, and we created what was called the open verification methodology. And so that, again, was a full SystemVerilog methodology. It would run on both Cadence's and our simulator. So it was truly open. Any SystemVerilog compliant simulator it would run on. And we were then competing with VMM with OVM. And what we noticed was we started to win, and Synopsys started to see their market share slipping. And so eventually they said, hey, we're going to throw in the towel. We're going to be part of the UVM. And so they updated VCS so that it was fully SystemVerilog compliant. And now all three major EDA vendors were all supporting SystemVerilog and the OVM. And sort of at that point, we figured methodology wars are over. Well, then what happened was the IEEE, who had created SystemVerilog, said, this is good stuff, let's make it a standard. And so they basically uprevved UVM 2.0, and instead of calling it, OVM 2.0, instead of calling it OVM 3.0, they renamed the standard as UVM. So that's where these things come from. So really, what is UVM? And it's mainly a class library. So it's a set of base classes that you can construct your test bench out of. It's a set of methodologies of, how do I construct my test bench? How does my test bench start up? What's the, how does it run through to completion? What is the messaging? How does it shut down? So all of that is included in the UVM, so you don't have to reinvent the wheel by just using the base SystemVerilog language. So it's all about interoperability and reuse. So you want to make sure that it works on every SystemVerilog compliant simulator, and you want to make sure that any objects that you create are reusable in different phases. So the base object of a UVM test bench is called an agent. So for every major communications port on your device, let's say you've got a PCIe port, a AMBA, an AXI bus, a USB bus, a SATA bus, any of these things, you would have an agent that you would take a UVM agent and you would turn it into, my custom bus agent. And so you would extend the agent to add all of the stuff that you do in that thing, in that protocol. And then the agent will have, at the very least, it will have a monitor that monitors the bus, turns that set of bit wiggles into transactions, feeds that back. That monitor will recognize those transactions and then feed them to the rest of your structure. Almost all of your agents will also have a sequencer, which generates sequences of transactions of that protocol type, hands them to the driver. The driver passes them over here to this thing called the driver BFM, which turns that from a transaction into bit wiggles that stimulate your device. And you might also have a coverage collector within the agent. You'll probably have a coverage collector for the high level, at the chip level. So one of the things that UVM is really good at is saying, hey, I want to use this agent in another test bench without needing to make changes. That's all been kind of built in. So it's, as I said, interoperability and reuse. All of the things in the agent take place at what's called the transaction level. So when you're debugging up here in the SystemVerilog world, you're debugging transactions. So this was an AXI read with all of these different parameters. If you want to, you can go down to the signaling level down here and look at what was happening at the signaling level, but it's a lot easier to debug at the transaction level if that is, when you're working at that level. So that's another thing that UVM does, is it raises that level of abstraction up. So, as I said, the agent has these pieces. At the very least, it probably has a monitor, maybe has an analysis component in it. The monitor will receive transactions and either analyze them locally or send them out of an analysis port for analysis at a higher level. Most drivers are active, and so they have a sequencer creating these sequences of events, and then a driver which drives those sequences, those transactions to your device. So if I was going to show you a little bit of UVM code, you know, here is an ARM APB bus. So you can see here's my APB agent. I declare that it has a monitor, a sequencer, a driver, and a coverage collector. You need to create this all in what's called the build phase. You need to define the connections down here in what's called the connect phase. Then there's a run phase that says, okay, let's run some things. If I wanted to push down and look at that driver code, you can see that I'm receiving tasks. I'm receiving things that I should be driving. And then you can see my monitor turns that into, you know, I need to set these signals. I need to wait a little time. I need to wait for a read to happen, grab the data, and, you know, go, etc. So that's the driver code. So again, there's the run phase. We get a transaction from the sequencer. We translate that into bit wiggles. The sequencer is just, you know, waiting till it gets to that point. It's randomizing. I can look at the actual sequence. You see what I'm randomizing. You see what the constraints are, etc. And at this point, my guess is you're probably feeling a little overwhelmed because there's a lot of stuff that goes into there. For every one of these agents, you know, I'm going to have all of these pieces. I'm going to have the agent. I'm going to have the driver. I'm going to have the monitor. I'm going to have the sequencer, the coverage collector. So for every one of these agents, it's probably 12 or 15 or some odd number of pieces that I've got to create. For the test bench itself, it's going to be a whole bunch of code. For the sequencer, it's going to be code. For all these different pieces, and you know, a lot of times I'll show this to customers, and they're like, I don't even know where to start. I don't know how I'm ever going to get to the point where I can do this. So that's really the question that gets asked is, how do I get started with SystemVerilog and UVM? And I would say there's a few ways that you can go about that. The first thing you have to do is you really have to decide you're embracing SystemVerilog and the UVM. You can't really dip your toe in because unfortunately, it is not an evolutionary methodology with your current test bench. You need to kind of throw everything away and go head first into the pool. So if you want to learn more than just that little bit that I just showed you, Mentor has a website called the Verification Academy. It is a free verification website. There are a whole bunch of courses that teach you different things, and then there's an online reference manual for UVM. I'd say there's a good book that was written by a person from Mentor, Ray Salemi, and he has written this book called the UVM Primer, and it is a really nice set of methodologies for getting started. But even better than that, there is a course on UVM Academy, our Verification Academy, and we have a methodology that we call the UVM framework, which is a way for you to take some shortcuts, to use some templates that we provide you to create your initial test bench and generate all that UVM code so that really, you know, it guides you to the 3 or 4 places that you need to go into, because most of that code is very boilerplate. And so using the UVM framework, it will generate your whole test bench for you, guide you to the 5 or 6 places that you need to go do some edits to add your value added stuff and get up and running as quickly as possible. And then the last thing is that Mentor has a catalog of verification IP, which are a bunch of prepackaged UVM components for standard protocols. So Verification Academy, if you search on Google for Verification Academy, that will definitely be your first hit. There are several courses: Introduction to UVM, a basic UVM course. There is now a UVM framework course, which is probably the one that I would now suggest you start with first. And then once you're up and running a little bit, there is the UVM cookbook, which is an online reference manual. A couple of suggested books. Like I said, Ray Salemi has written a couple of books. The first one is called FPGA Simulation, and it's really a step-by-step guide of saying, hey, we're not doing a whole lot of simulation right now. Let's take a few steps to, get there. And then, once you've gone through that, and you progress to the point that you're pretty good with what's in this book, his UVM primer book is also a great resource. UVM framework, though, actually is probably what I'd say the best place to start these days. So the universal methodology, UVM, the universal verification methodology, that's all the raw materials that you're going to use to build your test bench. That's kind of SystemVerilog is maybe those raw materials. The UVM is, taking that a step further and putting some organization around it. But there's still a really large learning curve to getting, up and running with that. And so what the UVM framework does is it puts, even more automation on creating that and really guides you to getting started as quickly as possible with the UVM. So what it really is a jump start to get your test bench up and running as quickly as possible. And also it has built in all the reuse to make sure that all your building blocks can be, connected together at a higher level without any of the pitfalls of developing a UVM test bench from scratch. So what it really is for every agent that you're going to do, you create this template. And this is an example of the Python template that you can do. So what you say is, I have this floating point unit and I'm going to drive all of the control signals to this floating point unit. So my agent is called my FPU reg. I declare what all the ports going into and out of that agent are. And this is from the test bench point of view. So the two inputs to the FPU are outputs from the agent. The result coming back from the FPU is an input back into the test bench. And then you have maybe a start signal, a ready signal. I think I probably should put an operation signal here, which I hadn't, but you kind of get the idea. So you start from this template. You create one of these templates for every agent that you're going to have in your design. You create a template for the test bench itself, the environment, and you create a template for an initial test that you're going to run. So it's 4 simplified templates, and you pass it to this code generator, which then will go and generate, all those dozens and dozens and dozens of files, create your entire test bench, create all the file lists and the make files for compiling and getting that test bench running. And what comes out of here is actually a test bench that you can run the make file. It will compile it. It will launch the simulation. It will basically, have a runnable test bench. But there are some tasks that you're going to have to do. So for instance, you're going to have to go into the driver and fill out the signaling for when that driver receives a transaction, how does it transmit it? You're going to have to fill out the monitor. When I see these wiggles on this bus, that means I received a read operation, and here's what it was. You're going to have to go do a few constraints. So for instance, what you do is you can go and you can search through the text files, and you can find this UVM change me comment, and that's going to be, so here I have the driver BFM. It had a generic access task that it stuck in there, and so what I do is I go change that to a do read and a do write task. So when I get this operation, I do a read. When I get this operation, I do a write. When I do a write, what do? Well, I set these values. I set the write signal to a high, and then I wait until I get the ready signal back. I wait till this is not a 0, and as soon as that comes back, then I grab the data that came back, or then I can release the data because my write has finished. If I did a do read, I'd do the same thing, but I'd have the write. I'd wait till the ready came back, and then I'd grab the values on that bus. So what the UVM framework is really this jump start to get you running. You don't need to fully understand the UVM. You just need to generate the code, know that I need to make these 4 or 5 changes, and it gets it up and running as quickly as possible. We have, at this point, probably 50 different companies who are using UVM framework or more, and it really has become what I'd say is the best jumpstart for UVM that's out in the market right now. What UVM does is it gives you, as I said, this TLM debugging. So you get to look at everything at this higher extraction level. That's the other thing actually that ends up being put in there. When you go through that template and you create all this code, it automatically creates the wave.do file to bring all of those transactions into the wave window, so you can start doing that transaction level debugging as quickly as possible. So what UVM framework is it is a UVM jumpstart. It is a free open source tool. No licensing required to run it. All the code that comes out of it is runnable on any SystemVerilog compliant simulator. And it's really about getting you up and running in UVM as quickly as possible. So then the other place is, not only do you have the UVM framework to get your test bench up and running, but if you think about most FPGAs these days, there's probably a lot of custom logic that lives inside your FPGA. But as you go out to the I/O coming into your thing, it's probably standard things like UART and Ethernet and PCIe and SATA and all these other standard protocols like AXI. And so you're pushing data through these standard protocols, and Mentor provides a library of different standard protocols that are basically UVM agents to allow you to do that. So let's say on my device, I have, an AXI 4 bus, I've got a PCIe bus, I've got 10 gigabit Ethernet, and I've got a serial ATA and some memory interfaces on my thing. So I can go into this VIP category and I can drop down agents that are pre-created that I don't have to do anything with. And those agents will generate and monitor all the data that's driving into all my custom circuitry. You can use this at block level. So let's say your custom circuitry communicates on an AXI bus. You can go straight to that AXI and just create a block level test bench with an AXI and a RAM. If you want to drop out further, you can have a serial ATA that's driving through there to your custom data. So you can do this at many different levels, and basically, this is just something that gets you there as quickly as possible. For instance, with the PCIe, there's a full set of documentation. The PCIe of the IP will automatically, start the training phase. As soon as you reset the device, it'll go into a training phase. It'll get through the training phase, and then you have the API to create all the transactions that you want to do on that bus. This has got even, more sophisticated debug at that high level TLM level. And basically, what each of these is an agent. It has all the text sequences you're going to need. It collects all the coverage you're going to want for that. It starts with a coverage plan so that you can make sure that the different features that you need in your device have been tested. You have a full set of sequences that you can drive to that bus, and then you get a full coverage plan so you can see, hey, I've tested all of these things. There is a graphical configurator for creating these pieces of the IP. So basically what you do is you say, hey, I've got an AXI bus. You go through and you set the options for that particular thing. So in this case, I'm going to say, I'm driving an AXI slave. I have a 32-bit address, a 32-bit data. Some of the other pieces of the IP have more complicated configuration. You can hook up the wires to different things, get that all, drive it to your bus. There is a way then to include these these Quest of the IP pieces in your higher level test bench if you have some custom IP that you've created with the UVM framework, so that the two technologies work really well together. And basically the mentor of the IP helps you to get a rapid start with your UVM test bench. The UVM framework allows you to create custom agents, and we've found that we can get customers with absolutely no SystemVerilog experience up and running with the UVM in a really short amount of time. So with that, I just want to say thanks for listening in on the webinar.